Hi students, welcome back. This video is all about the determinants. In this video we are going to see what is the definition of a determinant, the properties of determinant, minors and cofactors, factor theorem, multiplication of determinants, area of triangle and collinearity, a simple topic, the special determinants, differentiation of determinants and what is Cramer's rule and the consistency of linear equations, adjoint and its properties, inverse, characteristic equation and Hamilton's theorem, and system of equations and criteria for consistency. Now first let us see what is the definition for determinants. The determinant of a matrix is a scalar value that can be computed from the elements of a square matrix, and it provides the information about the matrix properties such as whether it is invertible or not. For a square matrix A, the determinant is denoted as determinant of A. For example, we take a determinant, a matrix A, which has only a single element, that is, it is of order 1, and then the determinant of A will be just is equal to B. Next, if A is a square matrix of order 2 and A is equal to, for example, we take the elements as A11, A12, A21 and A22, then the determinant of A will be is equal to A11 into A22 minus A21 into A12. Next, prop 2, 3 minus 4, 5. 3 minus 4, 5, 1, 1, minus 2, 2, 3 and 1. We have to find the determinant here. The order of the matrix is of order 3 by 3. Then the determinant of the matrix can be taken as determinant of A is equal to determinant of 3 minus 4, 5, 1, 1, minus 2, 2, 3 and 1. Value of the determinant is given by is equal to, for the first element takes the plus sign, the second element takes the minus sign, and the last column takes the plus sign. Now 3 into the minor of 3. Minor of 3 is given as minor in the sense deleting the first column and the first row. The remaining elements are written inside the determinant as 1, minus 2, 3 and 1. Minus, this element takes the minus sign and therefore I give minus. Minus of minus 4 into the next elements, deleting the second column and the first row. The remaining elements are written inside the determinant as 1, minus 2, 2, 1 plus 5 into deleting the corresponding column and the corresponding row. The remaining elements inside the determinant are written inside the determinant given as 1, 1, 2, 3. Now we find the value of the determinant, which is equal to 3 into multiply 1 into 1 is 1, minus of 3 into minus of 3 into minus 2. So plus 6 minus of minus 6, which is equal to plus 6. Minus into minus gives us plus here. Next, this element multiply 1 into 1 is 1, minus of 2 into 2. So this is plus 4 into 1 plus 4. Next, plus 5 into 3 minus 2. So the value of the determinant will be 3 into 7 plus 4 into 5 plus 5 into 1, which is equal to 21 plus 20 plus 5, which is equal to 46. This is how we find the value of the determinant. Next, coming to the determinant, the previous example what we have taken, A is equal to the first column is 3, 1, 2, second column minus 4, 1, 3 and the third column is 5, minus 2, 1. Suppose I change the value of the determinant is unaltered if rows and columns are interchanged. I am going to interchange the rows and columns of the determinant. The determinant so formed will be is equal to the first column becomes the first row. So I write it as 3, 1, 2, second column minus 4, 1, 3 and the third column comes to the third row 5, minus 2 and 1. The value of the determinant here, the determinant is given by parallel lines. Elements inside the determinant are given in parallel lines, and therefore the determinant of B, when we expand the determinant, the value of the determinant will be the same, 46. So you can try this example. Interchange the rows and columns of any determinant. The value of the determinant is unaltered. This is the first property. Second property, if any two rows or columns of a determinant are interchanged, then the determinant changes its numerical value and the the numerical value is unaltered, it changes its sign alone. For example, in this given determinant, we take D is equal to A1, B1, C1, A2, B2, C2, A3, B3 and C3. Here the first row and the second rows are interchanged. So D1 here, A2, A1, A2, A1, B1, C1 comes to the second row here, and therefore we give the minus sign for the determinant. This is minus of D. Here D1 is equal to minus D, or we can say D is equal to minus D1. The value, for example, the previous example we can take. The previous example, this B determinant is taken. For example, I interchange the first two rows of the determinant. Then the B1 determinant will be is equal to determinant of minus 4, 1, 3, 3, 1, 2, 5, minus 2 and 1. Expanding the determinant, the value of the determinant will be minus 46, where the numerical value is unaltered and the determinant changes only its sign. If all the elements of any row or column are 0, then the value of the determinant is 0. For example, we take the determinant 7, 8, then the value of the determinant is 0. If all the rows or columns of a determinant are proportional to the element of any other row or column, then the value of the determinant is 0. So taking this example, if D is equal to A1, A2, A3, B1, B2, B3, C1, C2, C3, then if any row or column of a determinant is proportional, for example, I take 1, 2, 3, the next row is 3, 6 and 9, then we take any other row as minus 1, 2, 4. Now, what about this row 1 and row 2? R1 is proportional to R2. R2 is nothing but R2 is equal to 3 times of R1. So we say R1 and R2 are proportional. Therefore, the value of the determinant is directly is equal to 0. D is equal to 0 here. Multiply, for example, all the elements of the determinant by some scalar k. Then the value of the determinant itself is multiplied by the same scalar k. For example, we take a determinant 1, 2, 3, 5, 6, 7, 8, 9, 10. If any row is multiplied by 2, for example, multiply the first row by 2, 2, 4 and 6. I multiply R1 by 2. Multiply R1 by 2. Then the determinant can be written as 2 times of 1, 2, 3, 5, 6, 7 and 8, 9 and 10. Any row or column is multiplied by the scalar k, then the determinant itself is multiplied by the same scalar k. If all the elements of the row are proportional or identical, then the value of the determinant happens to be 0. If the element is expressed as sum of two terms, then the determinant itself is expressed as sum of two determinants. For example, in the given determinant, the first row, all the elements are sum of two terms, a1 plus x, b1 plus y, c1 plus z. So it is expressed, the first determinant is expressed with a1, a2, a3 as the first column, b1, b2, b3 as the second column, and c1, c2, c3 as the third column. So this is the first determinant, plus we take the next determinant, that is nothing but is equal to a1, first row is x, y, z, second row is a2, b2, c2, and the third row is c, and the third row is a3, b3, c3. The first row is x, y and z. So if any row is expressed as sum of two quantities, the determinant itself is expressed as sum of two determinants. Next property, the value of the determinant is unaltered by adding any other row of column of the same multiples of the corresponding row or column of the determinant. For example, I take a determinant D is equal to, for example, D is equal to 1, 2, 3, minus 1, 0, 5, 6, 8 and 10. Then this determinant will be is equal to, I multiply R2 with R2 plus 2 times of R2 plus 2 times of R1. I am going to change the second row. First row will remain as it is. The second row, and adding with, multiply the first row, add with second row. So 2 into minus 1 gives us minus 2. 2 into 2 is 4. 4 plus 0 gives us 4. 3 into 2 is 6. 6 plus 5 gives us 11. 6, 8, 10. Then the value of the determinant is unaltered. Here we have multiplied, in this example I have multiplied the second row with factors. What is a minor? A minor of an element Aij of a determinant of order n is of a square submatrix of order n minus 1 obtained by leaving the ith row and the jth column. Minor of Aij is denoted by Aij. For example, we take a matrix A is equal to the elements of order. I take the matrix of order 3 by 3, A11, A12, A13, A21, A22 and A23 and A31, A32 and A33. I want the minor of the element. A11. So minor of M11 is given by is equal to the elements leaving out the corresponding row and column. The remaining elements are taken. So A22, A23, A32 and A33, which is equal to the product of A22, A33 minus of A32, A23. For example, we can take an example here. If A is equal to the matrix 1, 2, 5, minus 1, 0, 4, 3, 1, 1, I want the minor of 2, 3. 2, 3 element here is 4. I want the minor of 4 here. So the minor of 4 will be is equal to, deleting this corresponding row and column, the remaining elements taken here. This is equal to 1, 2, 3, 1, which is equal to 1 minus of 3 into 2 is 6, which is equal to minus 5. This is a minor. Next, coming factor of an element Aij denoted by capital Aij, or it can also be denoted as Cij, which is equal to minus 1 whole power. Aij is equal to minus 1 whole power I plus j into Mij. It is a signed minor. For example, we take a matrix A which is equal to of order 3 by 3, A11, A12, A13, A21, A22, A23 and A31, A32 and A33. We are going to find the cofactor of the first element. Cofactor of this element, here I is equal to 1, j is equal to 1. So 1 plus 1, this element takes the plus sign. 1 plus 2 minus 1 whole power 1 plus minus 1 whole power 1 plus 2 is equal to 3 minus 1 whole power t takes a minus sign. The next element will take the plus sign. The next element, this element 2 plus 1 is 3, takes the minus sign, plus sign, minus sign, plus sign, minus sign and then plus sign. Now I want to find the cofactor of any of the element we can take. For example, I want to find the cofactor of A23. That is the cofactor of A23, or it can be written as A capital A23. That is nothing but the cofactor of A23 element will be is equal to minus of, if this element takes the minus sign, so it takes the minus sign, so I write it as minus of, deleting the corresponding row and the corresponding column. The remaining elements are written A11, A12, A31, A32. This gives me the cofactor. For example, we can see one example here. For example, we take matrix A is equal to 1, 2, 3, 4, 5, 6, 1, 1, 1. I want the cofactor of 4. The sign, what is the sign it takes? Plus, minus, plus, minus, plus, minus, plus, minus, plus. So the sign it takes, both this element takes the negative sign. Cofactor of 4 will be is equal to minus of, deleting the corresponding row and column. The remaining elements written 2, 3, 1, 1, which is equal to 2 minus 3 is equal to minus 1. So we get the cofactor. Next, note that the sum of the product of the elements of any row or column with any other corresponding cofactors is always equal to the value of the determinant, and the elements of a row or column are multiplied with the cofactors of any other row or column, then the sum is 0. For example, we can give an example here. I take a given determinant. For example, we take delta is equal to, I take the elements as A1, B1, C1, A2, B2 and C2, A3, B3 and C3. The elements of the cofactors of A1, B1 and C1 are given by capital A1, B1 and C1 are said to be the cofactors of the corresponding elements of A1, B1 and C1 in the given determinant. Then the product of the matrix, the given determinant and its cofactor determinant. Cofactor determinant is given in, the elements are in the form of capital letters A2, B2, C2, A3, B3 and C3 into the product of the cofactor determinant. Cofactor of A1 element is denoted by capital A1. So A1, B1, C1, A2, B2 and C2, A3, B3, C3 will be is equal to, when we make the row by row multiplication, I make the multiplication here, first row and the first row here. So the elements will be A1, A1 plus B1, B1 plus C1, C1 we get is equal to delta. The other elements will be 0 and this is 0, 0, 0 and delta. What is this delta? This is what we see in a note, sum of product of elements of any row with the corresponding row, cofactor row, then it will be equal to the value of the determinant. This A1, B1 and C1 we multiply with the first, for example, A1, A1 plus B1, B1 plus C1, C1. First row and the first row is multiplied. Next multiply first row and the second row. So when we multiply the second row, we get A1, A2 plus B1, B2 plus C1, C2. Next first row and the third row we multiply A1, A3 plus B1, B3 plus B1, B3 plus C1, C3 and similarly the next two rows we multiply, then the value will be is equal to delta 0 and 0. This is what given in the note. The elements with the corresponding cofactor elements, the sum of product of any row with the corresponding row will give us the value of the determinant, which is equal to delta. Then the product with any other row or column we multiply, then the sum is equal to 0. Next, moving on to adjoint of a matrix, adjoint and its properties. What is adjoint? Adjoint is nothing but the cofactor transpose of the cofactor matrix. So we can write adjoint of A is equal to Aij whole transpose. So here we have the property A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I. I is the unit matrix. If A is not equal to 0, then we can write it as A into Aj by determinant of A is equal to I, where I is a unit matrix of the same order of A. For example, here there is a shortcut. This is equal to if the matrix on diagonal elements, and so the element will be is equal to minus B and minus C. This is adj of A. Properties of adjoint of A given as a determinant of adj of A is equal to determinant of A whole power n minus 1. Adj of aj is equal to determinant of A whole power n minus 2 into A, and where determinant of A is not equal to 0. Determinant of adj is given by determinant of A whole power n minus 2 the whole squared. Then adj of AB can be written as adj of B into adj of A. Adj of a scalar into A is equal to k power n minus 1. It can be written as k power n minus 1 into adjoint of A, where k is a scalar, any number. Adjoint of A transpose is equal to adj of A the whole transpose. These are the properties of adjoint of A. Next, moving on to inverse of a matrix. A square matrix A is said to be invertible if and only if it is non-singular. Matrix is non-singular. That is, for any given matrix, if the determinant is not equal to 0, then we say it is non-singular. To find A inverse can be given as A inverse is equal to adjoint of A by determinant of A. And another, with this adjoint of A by determinant of A, how did we get this? This is A into adj, we know the result. A into adj is equal to adj into A is equal to determinant of A into I. Pre-multiply by A inverse on both the side. A inverse into A into adj will be is equal to A inverse into determinant of A into I. A inverse A we know is equal to I. Therefore, we can write A is equal to A inverse determinant of A. I is the unit matrix here, and therefore we want A inverse. So A inverse can be written as is equal to adjoint of A divided by determinant of A. Moving on to the properties, AB whole inverse is equal to B inverse A inverse. The inverse of a product of two matrices is equal to product of the inverses taken in the reverse order. A inverse the whole transpose is equal to A transpose the whole inverse. A inverse whole inverse is equal to A, and A inverse whole power K is equal to A power minus K. If A is non-singular, then determinant of A inverse is equal to determinant of A whole inverse, and this is possible only if determinant of A is not equal to 0. If an idempotent matrix is invertible, what is an idempotent matrix? Idempotent matrix if A power n is equal to A and determinant of A is either 0 or 1, then we say it is an idempotent matrix. So here for an idempotent matrix is said to be invertible, inverse exists. If is invertible, then its inverse will be an idempotent, is an identity matrix. If an idempotent matrix is invertible, its inverse will be an identity matrix. An idempotent matrix will not be invertible because its determinant value is 0. Orthogonal matrix is always invertible. A inverse is equal to A transpose. A is equal to A inverse for an involutory matrix. Involutory matrix, what is involutory? Involutory is A square is equal to I, then A is equal to A inverse. Cancellation loss, AB is equal to AC implies B is equal to C. This is left cancellation, and B is equal to C implies B is equal to C, which is the right cancellation law. What is the characteristic equation? Let A be a square matrix and determinant of A minus xi. X is a scalar here, can also be written as A minus lambda I is called a polynomial of A, and the equation determinant of A minus xi is equal to 0 is called a characteristic equation of A. After solving the characteristic equation, the polynomial values of x are said to be the characteristic roots of the polynomial, and sum of the roots of the characteristic equation is equal to the trace of the matrix. Trace of the matrix is nothing but the sum of the diagonal elements. Product of the roots of the characteristic equation is the determinant value, and degree of the characteristic equation is same as the order of the matrix. Let us see next what is a Cayley-Hamilton theorem. What is this Cayley-Hamilton theorem? For every square matrix A satisfying the characteristic equation, the characteristic equation is A minus xi is equal to 0. For every square matrix A satisfying the characteristic equation, then A inverse is given by A inverse is equal to minus 1 by an into A naught A power n minus 1 plus A1 A power n minus 2 plus goes on plus A n minus 1 into I. Let us see an example for this. For example, I take a matrix if A is equal to, matrix A is equal to 1 2 0 2 minus 1 0 0 0 minus 1. We use the Cayley-Hamilton's theorem here, and to show that we are asked to show that 5 times A inverse is equal to A square plus A minus 5i. We are going to use the Hamilton theorem here. If we have the characteristic equation, what is the characteristic equation? Determinant of A minus xi is equal to 0. Therefore, the given matrix becomes, that is, we get the matrix in the form of determinant of A minus xi means the values of the diagonals we give it in the form of 1 minus xi. So x 1 minus x 2 0 2 minus 1 minus x 0 0 0 minus 1 minus x. This is the determinant of A minus xi. Now this is equal to 0. Expanding the determinant and simplifying, we get the equation x cube plus x square minus 5x minus 5 is equal to 0. Theorem here, and then we write, so now substitute the value of x as A here. So which gives us A cube plus A squared minus 5A minus 5i is equal to 0. We have to show here 5 into A inverse is equal to A square plus A minus 5i. Therefore, I want here A inverse, 5 times of A inverse. So what we do here, 5y can be written as 5y is equal to a cube plus a square minus 5a. Multiply by a inverse on both the side, we get 5a inverse is equal to a cube into a inverse gives us a squared plus a square into a inverse gives us a minus 5 into I. So this is using the Cayley-Hamilton theorem, we are able to find what is the inverse here. Next, moving on to system of equations and criteria for consistency. System of D3 are the three linear equations. We take delta here, delta or D, which is equal to the coefficient of x, y and z in the three equations, a2, b2, c2 and a3, b3, c3. Now, we are going to find whether this delta is equal to 0 or not equal to 0 to find the consistency for the system of equation. We say the system of equations are consistent only if delta is not equal to 0. Expand the determinant and it is not equal to 0. Then we say D is not equal to 0. We apply the Cramer's rule here and say the system of equations are consistent having unique solution. D1 is not D1, D2 and D3. All the three are not equal to 0. Then we use the Cramer's rule to find what is x. X is equal to D1 by D, y is equal to D2 by D and z is equal to D3 by D. What is this D1? D1 will be is equal to the constants of the linear equations are being represented in the first column, are replaced in the place of x in the first column. So it can be written as D1, D2 and D3 and the second two columns remains as it is. B2, B3, C1, C2 and C3. Then similarly for D2 the second column is replaced, consistent having unique solution. Suppose this D is equal to 0. Suppose D is equal to 0. Delta is equal to 0 and delta 1, delta 2, D2, D3 all are equal to 0. Then we say the system is consistent having infinite number of solutions. Suppose D is any one of Di. Suppose if any one of either D1, D2 or D3 are not equal to 0, we say the system of equations are inconsistent having no solution. If homogeneous equations, what are homogeneous equations? A1x, all the constants are 0 here. Then we say the system of equations are homogeneous. For homogeneous, determinant of A is not equal to 0. Then x, y, z are all 0. A capital X matrix, that is the variable matrix, is equal to 0. We say the system of equations have trivial solution. That is x is equal to 0, y is equal to 0 and z is equal to 0. Suppose determinant of A is equal to 0. The system has infinite number of solution. It has infinite number of solution, or you can say it has non-trivial solution. Therefore, for non-homogeneous equation, if delta is equal to 0, then we use the Cramer's rule and we say the system of equation has a unique solution. That is one solution for x, one solution for y and one solution for z. If delta is 0, delta x, delta y, that is D1, D2, D3 all are 0, then the system is consistent having infinite solution. If delta is 0 and delta x, delta y, delta z, D1, D2, D3 all are 0, 2 by 2 minus of delta is 0, but any one of the 2 by 2 having no solution. Area of a triangle with vertices x1, x2, x3 are given by delta is equal to half into determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1. The points x1, y1 are written in the first two columns. Last column is 1, 1, 1. Then this is the area of the triangle if this is equal to delta, and if this is a property of area of a triangle. Next, moving on to transpose of a determinant. What is transpose of a determinant? For example, we take D is equal to the determinant A1 B1 C1, A2 B2 C2, and A3 B3 C3. Then the transpose of the determinant D transpose will be is equal to the first column becomes the first row, and that is A1 A2 A3, B1 B2 B3, and C1 C2 C3. This is transpose of a determinant. Next, coming to the special case of determinants, under that symmetric determinant. What is this? If D is equal to D transpose and the Aij will be is equal to Aji, then we say the determinant is a symmetric determinant. For example, symmetric determinant, we can take determinant of -2 3 -1, then 1 2 is equal to A2 1, A3 1 is equal to A1 3 is equal to A3 1, and A2 3 is equal to A3 2. Therefore, we say it is a symmetric determinant. Next, skew symmetric determinant. If D transpose is equal to -D, then we say the determinant is a skew symmetric determinant, and Aji is equal to minus of Aij. For example, we can take the determinant where determinant diagonal are all 0, and the elements A12 element is equal to A21 and A13 is equal to A31. A12 is equal to minus of A21 and A13 minus A13 is equal to A31, and this A23 element is equal to A minus of A32 element, which satisfies the condition Aij is equal to minus Aij. Therefore, this is a skew symmetric determinant. Integral powers of x and two rows or columns become identical when A is substituted for x, then x minus A r power r minus 1 is a factor of D. Example, we take a determinant here. Solve. The determinant is equal to 0. Now I put x is equal to 0 in the given delta. What happens to delta? Delta is equal to ABC. Third row becomes ABC. 3 rows are identical here. Therefore, according to the definition, x minus 0 the whole power r is the number of rows, 3 minus 1 becomes the factor of D, which implies that x minus 0 the whole squared is a factor of delta, or equating it to 0, we say x is equal to 0, 0. Values of x are 0, 0. But here in the principal diagonal degree is equal to 3. There must be one more factor here. So on taking values of x here to be is equal to, on substituting again, put x is equal to minus of a plus b plus c, then also delta becomes 0, and therefore we can say that x is equal to, the roots of the equation are, the roots of for x are x is equal to 0, 0, minus of a plus b plus c. So this involves the factor theorem. Let us see a question here. The value of the given determinant is dash. There is a shortcut to find the value of the determinant. Let us see the degree of the leading diagonal, principal diagonal here. The degree of b plus c is 1, c plus a is 1, a plus b is 3. So the degree of the leading diagonal is 3. Now in the given options, the product must be, the degree must be 3. First one, degree is not equal to 3. The second one, here 1, 2, 3, 4, degree is not equal. Product of the factors, the degree is not equal to 3. Degree is equal to 4 here, and this is also not the answer. None cannot be the answer, and therefore the answer will be is equal to 4. We see the determinant is equal to the right hand side. We have x minus y, y minus z, z minus x, 1 by x plus 1 by y plus 1 by z. There is a super shortcut to find this n here. We see the degree of the principal diagonal. the degree of the principal diagonal is n plus 2 plus n plus 3. Degree of z is n plus 3, which is equal to 3n plus 5. Now check the right hand side. X minus 1 degree is 1, y minus z degree is 1, z minus x degree is 1. This is 1 upon x, so less 1 degree. So 3 minus 1 will be is equal to 2. Equate 3 minus 1 to 2. Now 3n is equal to minus 5 plus 2. Now 3n is equal to minus 3, and therefore we say n is equal to minus 1. Therefore the answer is B, which is equal to minus 1. Another determinant, if this determinant is equal to 0, given the determinant is equal to 0 if 4 options are given. So here let us take C1 is equal to 0. Substituting C1 is equal to 0, we get xp plus y is equal to 0 implies here p is equal to minus y by x. Similarly, yp plus z is equal to 0 implies p is equal to minus z by y. Now take the product, p and p here are equal. Minus y by x is equal to minus z by y, which implies y square is equal to xz. Y square is equal to xz if x, y and z are in GP. Then we say that y square is equal to xz. Therefore the option is x, y, z are in GP. Next topic is differentiation of determinant. Let us take if derivation for that. D by dx of delta will be is equal to, differentiating the first row is nothing but r1 dash, r2, r3 remains the same, plus r1 remains the same, differentiate the second row, and third row remains the same, plus the last one r1, r2 remains the same, differentiation of r3 gives us the differentiation of the given determinant. Or it can column wise, it can be written as d by dx of delta can be written as is equal to differentiation of the first column, second column, third column remains the same, plus c1 into c1, c2 differentiation, c3 plus determinant c1, c2, c3 differentiation. This is differentiation of determinants. Next, multiplication of determinants. We have seen either it is a row by column multiplication or can do by row multiplication can be done for determinant, or column by column multiplication can be given for a determinant.